Hello everyone, I am Ranjani Sundaram and today I will be presenting a short summary of our paper, Efficient Distribution of Quantum Circuits. This paper is a joint work with Professor Himanshu Gupta and Professor C.R. Ramakrishnan from the Computer Science Department at Stony Brook University. We will first go over some background in quantum computing, what entanglement is, why distributing quantum circuits is important, and things that need to be done after distributing a quantum circuit. Then we will introduce the problem of distributing quantum circuits among a given network of quantum computers. We will go over various algorithms we used for this problem and the results we have obtained. Quantum computing is a novel method of computing using quantum mechanics. It has a high capacity to perform certain classical computing more efficiently. The idea behind quantum computing is that it performs calculations based on the probability of an object state before it is measured. Therefore, it has the potential to process exponentially more data compared to classical computers. Some of the applications of quantum computing include cryptography, search problems, machine learning, and computational biology. Okay, here we see the state of a single qubit. Alpha naught and alpha 1 are the amplitudes, which are complex numbers but are usually real numbers. The state X is a superposition of the basic states 0 and 1. When measured, X yields 0 with probability of alpha naught square or 1 with the probability of alpha 1 square. Therefore, we have alpha naught square plus alpha 1 square equal to 1.
Suppose we have a 2-qubit system instead. The first system that we see behaves in a way that we expect it to. Namely, 0, 0 occurs with a probability of alpha 0, 0 squared, 0, 1 occurs with the probability of alpha 0, 1 squared, etc. Now consider the second case. Here, the state cannot be decomposed as the state of the first qubit and the state of the second qubit. Additionally, if the first qubit measures 0, the second qubit state collapses to 0. This is called as an entangled state. This will come up later when we distribute quantum circuits. What is a quantum circuit? It is simply an abstract way of representing quantum programs. Quantum circuits consist of two entities, qubits and gates. Qubits are quantum equivalents of bits, as we have seen before. Gates are coherent operations that change a qubit between states. In this example circuit, Q0, Q1, and Q2 are qubits. C3 is a classical bit. H here is a unary gate. These two line segments with a plus in them are binary gates. The first one has Q0 and Q1 as its operands, and the second one has Q0 and Q2 as its operands. Once all three gates are executed, the three qubits are measured. We use a notion known as a universal gate set. Basically, a set of gates is a universal gate set if any quantum computation can be expressed by a circuit that only uses gates from that set. It is known that the binary gate called CZ, along with the universe of all possible unary gates, form a universal gate set. From now on, we assume that all circuits provided as inputs consist of only unary and CZ gates. In this example, you can see that the circuit contains only CZ and unary gates. These line segments are CZ gates and the boxes are unary gates. So why do we need to distribute a quantum circuit? The reason is current quantum computers cannot simultaneously hold a large number of qubits. In fact, as the number of qubits increases, protecting them from environmental factors becomes challenging. Therefore, distributing a quantum circuit could be a way to overcome this obstacle. In general, this is done by partitioning the qubits with each partition located in a different quantum computer. This could result in some CZ gates having their operands in different partitions. Unary gates won't have such problems. What we do is execute the resulting non-local CZ gates via quantum communication. So in this particular figure, Q1 to Q5 are qubits. Q1 is in partition 1, Q2 and Q3 are in partition 2, Q4 and Q5 are in partition 3. All these red CZ gates are non-local CZ gates since their operands are in different partitions. This green CZ gate B is a local CZ gate since both its operands are in the same partition P2. There are many kinds of quantum communication. The most obvious one is to transport a qubit physically from one quantum computer to another. This, however, is difficult. Instead, some forms of communication exploit the concept of entanglement that we saw before. First, there is a teleportation of a qubit Q from computer A to computer B. This assumes the two computers A and B each have one qubit from an entangled pair. Local manipulation of Q with the entangled qubit and some classical communication allows the teleportation of Q from A to B. Note that this teleportation destroys the qubit in A. A second, more recent form of quantum communication is called cat entanglement. Here, the cat entangler allows the qubit Q to be copied, so as to speak, across multiple computers. So these are linked copies. The copies can be simultaneously operated using CZ gates. Note that each copy needs an entangled pair. A disentanglement operation must be performed before a unary gate acts on Q. In the figure below, we see that a linked copy of Q1 is sent to partition 2 and to partition 3. These cat entanglement operations help execute this orange CZ gate and the blue CZ gate. Then they are disentangled before a unary gate acts on Q.
We now see the definition of the DQC problem. We are given a quantum circuit and k computers. Our goal is to distribute the given circuit equally among the computers and determine the communication steps so that the total communication cost is minimized. This problem is known to be NP-hard by reduction from the hypergraph min-cut problem. These are some of the related works regarding this problem. Azad et al. Consider different minimal forms of communications needed to execute non-local gates. They introduce a notion of cat entanglement and disentanglement. Martinez and Hunen posed the DQC problem as a balanced hypergraph partitioning problem. They prove that the DQC problem is NP-hard and give a heuristic based on hypergraph min-cut. We now introduce some terminologies related to our work. The first is the notion of migrations that represent cat entanglement operations. Migrating a qubit Q in a partition A to a partition B creates a linked copy of Q in partition B. We also say that a migration covers a non-local CZ gate if the migration facilitates the execution of this gate. We consider two versions of the DQC problem based on the kinds of migrations allowed. Suppose we are given a non-local CZ gate Q1, Q2. There are two kinds of migrations that help execute this gate. First, we can migrate Q1 to Q2's computer or Q2 to Q1's computer. Second, we migrate both Q1 and Q2 to a third computer and execute Q1, Q2 in the third computer. The first version of the problem we consider only allows migrations of type 1. This is called home cover as the gate is being executed in one of its operand's homes. The second version, called general cover, allows both kinds of migrations.
We first consider the home cover DQC problem. Our algorithm works in two steps. First, the qubits are distributed among computers using balanced k-min-cut problem. Here, qubits represents vertices and the weighted edge between a pair of qubits represents the cost of separating these qubits. The second step of the algorithm is to select migrations that cover non-local CZ gates. We pose this as a set cover problem where migrations are sets and non-local CZ gates are elements. In fact, note that because only migrations of type 1 are allowed, every non-local CZ gate has to be covered by exactly 2 migrations. Thus, the problem is a vertex cover problem. Incidentally, the graph formed by the migrations and the CZ gates contains no odd-length cycles and is bipartite. Vertex cover in a bipartite graph can be optimally solved in polynomial time. Therefore, we have an optimal algorithm for the migration selecting phase of our algorithm in the home cover DQC problem. Overall, the algorithm performs well on large circuits and conserves the number of migrated qubits in a partition. Here, we see an example where the home cover restriction on migrations turns out to be costly. In the first figure, home DQC algorithm migrates Q1 to partition 3, Q3 to partition 2, and Q2 to partition 1. So this requires 3 migrations to cover 3 gates. Whereas, if we allow migrations of type 2, if we migrate Q3 to partition 2 and Q1 to partition 2, that automatically covers all 3 gates. This third gate here between Q1 and Q3 is actually executed in partition 2. Recall that a gate Q1, Q2 may be executed by migrating both qubits to a third partition. Thus, 2 migrations may cover a gate together while the individual migrations may not cover the gate. Thus, the step 2 is no longer a traditional set cover problem, which means we need a more sophisticated algorithm for selecting migrations. The iterative because S of migrations that has the highest value of number of uncovered CZ gates that is covered by S divided by the size of S. This can be thought of some kind of value density, that is value of S divided by the size of S. In general, computing the above should take exponential time. However, we find a way of restricting possible collection of subsets that helps us solve each iteration in polynomial time. Essentially, each iteration can be solved using a weighted generalization of the densest subgraph problem. There is an optimal linear programming based algorithm for this problem. Overall, we give an order log n approximation algorithm for selecting a minimum set of migrations that cover all the CZ gates. So we evaluated the algorithms on randomly generated circuits and compared them with existing benchmarks. The parameters that we chose to vary include the number of qubits in a circuit, the number of partitions that the qubit is split into, the ratio of CZ gates is to unary gates in a circuit, otherwise known as fractions of CZ or frac CZ. We observed a 30 to 50% reduction in the number of cat entanglements used, with nearly 90% reduction in certain cases. This particular graph has x-axis is the varying fraction of CZ gates and y-axis is the number of migrations used. You can see that for low value of frac CZ, we perform similar to the existing benchmarks, but as the ratio of CZ gates increases, we perform extremely well. So the four algorithms, the bottom 4 algorithms here are our algorithms, and home cover and G star LP are the ones described in this presentation. These are some other results that we have obtained. The first column here are results corresponding to the value fraction of CZ equals 0.8, and the second column corresponds to fraction of CZ equals half or 50% CZ gates. You can see that when there is 80% CZ gates, our performance improves drastically with increasing number of qubits and increasing number of partitions. If you like our result and our work and would like to know more about it, please contact us. We look forward to meeting you in the conference. Thank you.